Hello everybody, welcome to another video lesson. Today we're going to be going over solving exponential problems using our logarithms, okay? That's our one objective for the day. Specifically, we're going to be looking at exponential decay and growth, okay? And then what's called logistic growth, all right? So we're not really learning anything new today. We're just applying everything that we've learned to these specific concepts of exponential growth and decay and logistic growth. All right, so let's hop right into exponential growth versus decay. All right, growth versus decay. So you guys have basically seen this before. Okay, exponential growth is going to look something like this. Okay, we've got f of t equals a e to the kt. You guys have seen this before, except our a. Okay, we previously kind of said that that was like a p-value, right? That was for continuous compound interest, okay? That was our initial principal investment, okay? But now that can be an initial value of anything where we have exponential growth, all right? So when we're talking, this is very useful for populations, okay? For atoms, molecules, things like that, all right? All right, and then we have exponential decay, okay? T again is in time, okay? Time in years. And then k is going to be this constant here. And the only difference between exponential decay and growth is that we have this negative value in our exponent, all right? We still have a e to the negative kt, and then for growth we have a e to the kt, all right? And then k is going to be a constant value here, and we are going to refer to that as either the rate of continuous growth or the rate of continuous decay. Okay, so if you're asked to find in an example problem, if you are asked to find the rate of continuous growth or decay, you are looking for that k value. All right, so just be aware of that. Okay, let's take a look at our logistic growth model now. Okay, this is good. This represents something with a limited capacity. Okay, so this is something that you could argue is a little bit more realistic, right? If we were to be creating something with a limited resource, right? A limited amount of ore or metal or whatever it is, okay? This would be a good way to represent that, all right? So we have this growth, but then we have this limited capacity that is going to kind of limit. We can't just go shooting off into infinity, and I'll show you a couple graphs there, okay? Again, I said this is good for modeling population growth, okay, because there's often a capacity on populations. And I want you guys to think about whatever that capacity is, that's going to be our horizontal asymptote, okay? So from a graph perspective, if you see exponential growth, right, that looks something like this, okay, just wherever your initial point is, and then it exponentially grows off into infinity, right? But for our logistic growth, okay, it has a similar start to it, right? We have this initial curve that's looking exponential, but then we are starting to reach our capacity, okay? Whatever this capacity is on our graph, that's going to be whatever horizontal asymptote we're approaching, all right? So just kind of keep that in mind if you were asked to, say, find whatever the capacity is or the equation for the capacity. You're really finding this horizontal asymptote that you can't really pass with your logistic growth. Okay, now the equation for our logistic growth, make sure you write this down, and then make sure you, if you didn't already, pause the video and write down the exponential growth and decay equations as well, okay? So we got f of t is equal to c over 1 plus a e to the negative bt, all right? Okay, a, b, and c are all constants, all right? And you'll typically be given these constants in a problem, okay? If not, you may be asked to find like one of the constants. Okay, the only difference is b is going to be in between 0 and 1. All right, but a, b, and c are all going to be positive. B is going to be in between 0 and 1. And then t is just going to be our time again. Okay, and t is our time like we saw in the exponential growth and decay models as well. All right, so let's go ahead and get into some examples here. We've got substance half-life. Okay, half-life of a radioactive substance is the time it takes for half of the atoms of the substance to disintegrate. The half-life of plutonium-239 is 24,000 years. Okay, determine the value of K. Okay, so really we're determining the rate of continuous decay, right? Okay, so we're looking at a decay model here, so we need to make sure we have this negative out in front of our exponent, all right? Okay, y is going to be our number of atoms, right, after a certain number of years. A is our initial amount of atoms, right, that we're starting off with. Okay, so how can we start an equation here we can solve for k? Well, I'm going to say, since we're looking at half-life, right, whatever y is going to be half, right, of our initial amount of atoms. Okay, so I'm going to set y equal to 1/2 a. Okay, and that's going to be equal to a e to the negative k 24th to the 24,000th. Okay, and that's because we've got this time of 24,000 years. All right, and again, we're looking at half-life. That's why we have this negative, or that's why we have this 1/2 a here for our y, for our number of atoms. Okay. All right, so we can go ahead and solve for k because our a's, since we have an a on both sides, if I divide by a, those cancel each other out. And hopefully you can see that I have 1/2 equals e to the negative 24,000k. We're going to go ahead and take the natural log of both of these sides. Okay, this is where our knowledge of logarithms comes into play. All right, and then this right-hand side, hopefully you can remember, is just going to simplify to whatever the exponent is. Okay, whatever my exponent is, so it's going to be negative 24,000k here. And then the natural log of 1/2, that's just some number, okay? So I'll go ahead and divide by negative 24,000 on each side. Now I can plug this whole side, left-hand side, into my calculator, and I'll find that k is approximately 2.888 times 10 to the negative fifth, okay? So that would be my rate of continuous decay there, okay? My k value. All right, now we're going to look at fossil dating, or carbon dating as it's otherwise known. Okay, so we've got a specimen that originally contained 42 milligrams of carbon-14, and it now contains 8 milligrams. Okay, and we are asked to see how old is the fossil. And we're given the carbon-14 K value right here. Okay, so we're given this K value. We're going to use this. Now we're using decay again. Okay, so I've got our equation for decay here. Okay, so my 8 milligrams, that's how much I have now. Okay, so that's going to be y, right? Okay, and then how much we started with, right? That's a, right here. Okay, and that was 42 milligrams. Okay, hopefully you can see that. 42 milligrams is what we started with. That's a, that's our initial. Okay, and then we're given our k value, so we can really just plug all this in. And whatever we find for t, that is going to be how old our fossil is. Okay. Now go ahead, make sure you're adding your units in here, just in case if they were to trick you and say, I don't know, this was 42 grams and now it's 8 milligrams. Okay, just make sure you're checking your units here. Okay, so I just added my units into our equation. Okay, so I'm going to divide by 42 milligrams on each side. Okay, so now I've got 8 over 42 is equal to e to the negative 0.00012 t. All right. Again, we're going to take the natural log of both sides. And notice I'm not plugging this in, so when I go to my next step here, okay, this simplifies to what we have on the right here, but I'm not plugging this into my calculator yet. Okay, and I'm doing that because I want to avoid any rounding errors, especially when I've got these numbers that are in the tens of thousands, or they've got 10 to the negative 6 power, right? Okay, you can easily find some rounding errors that are going to drastically throw off your problem or your solution. Okay, so don't plug this into your calculator until, okay, you get to this step right here. All right, because now my decimals cancel out here on the right hand side. Now I can plug this entire thing into my calculator. Okay, just as you see it right here. I'm going to plug everything like that into my calculator, and when I plug that in, hit enter, we'll find that this is approximately 13,819 years old. Okay, so again, if you had plugged in this natural log of 8 over 42, that's going to be something with a bunch of decimals, and that could mess up your final answer. Okay, 2 more problems here. All right, populations. Okay, we're given a type of bacteria that's growing exponentially according to this model right here. Y is equal to 1,000 e to the kt. T is our time in minutes now. Okay, T is in minutes. Important to recognize that. Okay, first, if there are 1,000 cells initially and 1,650 cells after 40 minutes. Okay, so that's our t value. Find the value of k for the bacteria. Okay, so we're solving for k. Okay, so now we're working with growth here. So I've got no negative sign here. Okay, I've got a positive exponent. And I can just plug in what I know, right? Okay, I know that what we have now is 1,650 bacteria cells. Our initial was 1,000, and we've been at it for 40 minutes. All right, so I can just plug everything in. I'm going to divide by 1,000, so we cancel out our thousands here. Coming up here, so I got 1.65 is equal to e to the 40k. Again, we're going to take the natural log because I got this e here, right? That's why I'm taking the natural log each time. So our right-hand side simplifies to 40k. We can divide by 40. Our 40s will cancel out. And then I can plug, again, what you see exactly right here into my calculator. That's what I'm plugging in. And I'll get that k is approximately 0.0125. Okay? Okay, we're going to use k to solve b, what we're asked for. Okay, suppose a second bacteria is growing exponentially according to a second model. Okay, so we're given y is equal to 50 e to the 0.0432t. Determine how long it will be before the number of cells of this bacteria exceed the number of cells in the other bacteria. Give me 1 second, someone's at the door. All right, sorry about that. Okay, so we are determining how long it will be before the number of cells of the second bacteria exceeds the number of cells in the first bacteria, okay? So what we need to do is set up an inequality is what we're going to do, okay? We're going to set up an inequality, and we're going to set the second bacteria, this function here, greater than our original function that we were given here, okay? Our original equation. Okay, so we've got our setup like so. We can go ahead and we're going to take the natural log of both sides right off the bat. Okay, I take the natural log of both sides right off the bat because why? Well, because I have this, I've got this property, right? That my product property here that says the natural log of a times b. That's going to be the natural log of a plus the natural log of b, right? Okay, so I'm going to kind of go in reverse there, right? Or I'm going to use this property and I'm going to kind of split these, right, with addition. So I've got the natural log of 50 times the natural log of e to my exponent here is greater than the natural log of 1,000 plus the natural log of e to my exponent here, okay? So hopefully you can see how we split that up because I've got this multiplication in between my 50 and my e's. Alrighty, so we can go ahead and start simplifying. So these are going to simplify to just the exponent, right? Our terms with our e in it, right? Our Euler's number. Okay, and then we can go ahead and get all of our values with t onto one side and all of our values without t on the other side. Okay, so I'm going to subtract by the 0.0125t on both sides, and I'm going to subtract natural log of 50 from both sides. And this is what we end up with. Okay, I can go ahead and simplify this a little bit because, again, going in reverse of what we have here with our quotient property, okay, natural log of a minus natural log of b is just going to be natural log of a natural log of a over b. Okay, so that kind of simplifies there a bit, and we can divide by the 0.0307. So our 0.0307 will cancel out, and we'll find that t is greater than 97.58 minutes, okay? So it will take about 97.58 minutes, okay, for the second bacteria population to surpass the first bacteria population, all right? Okay, last one. Now we're looking at our logistic growth. Okay, logistic growth. So we're given the population of a certain species of fish in a lake after t years, and it can be modeled by this function here, all right? Our population is p, and we're given 1880 in our numerator is equal to 1 plus 1.42 e to the negative 0.037t. Okay? And t is going to be greater than or equal to 0. All right. Okay, so someone went out, okay, some biologist went out maybe and studied these fish, and they were able to model what they found, okay, with this function here, okay? So first thing we're asked to do is we're asked to graph between 0 and 500, right? So we just need to plug this directly in to our calculators. Okay, so go to your calculator and set this up like so. And we can go ahead and I just want to show you guys what I put for window. Okay, so make sure you modify your window because it's asking for this interval from 0 to 500, right? Okay, so I want to set my y or my x value at 0 and 500. And I just increased the scale, okay, to 50. And I just kind of picked this arbitrary 2000. I did that because we've got this 1880 up here. Okay, so I picked 2000 for the y maximum and then 0 for the y minimum. All right, and I did that so we could get this kind of real world axes here, right? That's going to look like this. We're only working in quadrant 1 because we can't go backwards in time. You can't really have negative fish in a lake, right? Okay, so we're going to be working in positive time and positive population for our fish. All right, so if you go ahead and hit graph, you're going to get something like this. Okay, notice again, we've got this horizontal asymptote, right? Because there's some maximum capacity for the population of fish in this lake. Okay. Okay, what is the capacity of this fish in the lake? Okay, you can go ahead and hit trace on your calculator. And then if you trace and just go all the way towards the end, right, you'll realize that you are approaching, but you're not surpassing some y value. Okay, so I am approaching here as I go further and further towards 500. I'm approaching, but not surpassing 1,880. Okay, so keep that in mind. You can just hit calc and then value, and then maybe pick a large x value like 500 or 490, whatever. Okay, and that's going to give you your y value, which you'll notice is approaching some value, but again, it's not going to ever surpass whatever that capacity is. Okay. Okay, so again, with that knowledge there, we can determine that our fish capacity is going to be 1,880 fish. Okay. All right. When will the population reach 1,875? Okay. So one way to do this with your graphing calculator is to just set up another y equals. Okay. Set up y2 equals and just put y equals 1875. Okay. That's going to give you this horizontal line, right? Horizontal line, and then you can use your calculator to see where that intersects. Okay, now I know it's kind of looks like it's eventually becoming the same line, but it's really not, right? So if I go ahead and hit calculate our intersection, okay, it'll ask you for curve 1, you hit yes. It'll ask you for curve 2, you hit yes, you hit guess, and then it'll give you your intersection point. Okay, so it's going to intersect when y is going to, the population of fish will reach this 1875 at this value here, okay, at this x value. Okay, and remember, x is in time, and it's asking when will the population reach this value here, okay, this 1875, okay, and that's going to be at this y or this x value. And I know that's kind of difficult to see. If you go ahead and you were to really zoom in, you can kind of see where the blue is below, and then it comes above that horizontal red line. All right, so that's going to be about here at 170 years. Okay. All right, so that is all for today, guys. That is exponential growth and decay as well as logistic growth. Okay, good luck with your practice.